Okay, hi and welcome. Today we're going to go over this problem, which is given two non-negative integers m and n, find GCD mn. So we're going to practice the UMPIRE method to solve this problem. So the first step is to understand what we're doing. So to understand, we have the input. So the input is two non-negative integers. Is that right? Two non-negative integers, m and n. And the output is the GCD of m and n. So we have some examples here. Some examples include this example 1, which has an input of 6 and 9. And if you see what's divisible by 6 and 9, you see that the greatest common divisor of 6 and 9 is 3, so the GCD is 3. In example 2, we have the numbers 18 and 24. And if you go through all the divisors of 18 and 24 and you find the greatest divisor, then you will figure out that 2 and 3 are the greatest. 2, 3, and 1 are the divisors, and if you multiply them together, then you get 6. So the greatest common divisor is 6. So basically, now that we have a good understanding of the problem and examples of the problem, we can look at a match. So the match, what kinds of similar problems do we have? So this includes problems with involving algorithms and selection statements. So this particular problem involves Euclidean algorithm. So we can use that in our problem. And this problem also, in its most elegant form, requires recursion. So now that we have a match, we can go on to planning for this algorithm or for this problem. So the plan is that we have to consider the two corner cases if m equals 0 or n equals 0. Then we return. So we want to write a function. Okay, so a function that takes in m and n. So if m equals 0 or n equals 0, we want to return the max of m and n. And then if m is greater than n, then we want to return we want to learn what the algorithm is. So the algorithm is actually, if we write the algorithm up here, we see that if m is greater than n, then we can take division by n, which is of this form. So it's some greatest divisor q times n. So that's the multiplication that's less than m, and that adds a remainder. So now that we have that, we can show, or we can just set GCD m n is equal to GCD n r. So that's the formula for this particular problem. Okay, so we can, oh no. Oh, sorry. It looks like I pressed a button that wasn't that good. Okay, this is actually the implementation, so let me take it away for a second. So let me just go back to the plan. We were on the plan. So the plan was that we have a given algorithm given mn, then we have m equals some quotient times n plus a remainder. And then we have then the Euclidean algorithm says that GCD mn equals GCD and R. Okay, so we have given, we have if m or n equals 0, that we have to talk about that case first. We want to return max mn, and then if m is greater than n, then we want to set r equals m mod n, and then we return the GCD of nr, and then else we have these other case. We have where r equals n mod m, and then we return GCD mr otherwise. So now that we have the plan, we can implement this plan. So we want two inputs, so m equals int input and n equals int input. And then we want to define a function GCD mn such that if m equals 0, then we return n, and if n equals 0, then we return m. And then if m is greater than n, then we set r equals m mod n, and we return the GCD of m and r, and else in the other case we have r equals n mod m, and we return GCD mr. So we have that, and now we can print out the GCD, and then we're done. So we go through code check and we pass all tests. So that's the solution. So now we can go through a review of this problem. So we can go look at the review in Python tutor. So what do we have here? So we have the solution here. And then we want to step through the process. We have two inputs, 45 and 36. And then we print the GCD, and then we go into the loop, into the definition. We don't have any n or m equals 0. And if m is greater than n, so 45 is greater than 36, so then we output m mod n, so we have a remainder, which is 9, and then we return the GCD. We go up to the GCD of 36 and 9, and we output the next remainder, which is 0, and then we go to the GCD of 9 and 0, and then we output 9 as the return value. So there we have it. We have a review of this problem for the numbers 45 and 36, and the solution is 9. And now we can go back and talk about the evaluation. So the evaluation here is going to be a time complexity of O log min AB. And you can figure this out by comparing to Fibonacci numbers. Comparing A and B to Fibonacci numbers. I'm sorry, keep on going back and forth like this. So the final, let me go back to the final implementation. So, so as I've said here, evaluation, I'm gonna write it, just write it again. So the time complexity is O log min AB, and the space complexity, since we use no space, then is just O1 is auxiliary space complexity. So that's about it. Thanks for listening.